Today, today's topic is linear regression. So, um, what's so let me recall what we did the last time before going to this new topic, and then I will introduce the linear regressions. So, last time, what we did was like introducing the correlation coefficients, and so we were working on bivariate data, bivariate numeric data. So, and we introduced three measures for the correlation. One was like the Pearson's row, which were like the most used. Like it was very good for linear data. So that data that distributes as a cloud of points. I don't know, for instance, this one that I'm going to write. So if x is normally distributed and y is like x plus an exponential, let's say, we can try to plot x and y and see, like for this kind of data, I mean, there are some outliers because the exponential is like a positive, value, but for this data, like the correlation between x and y, the standard one is the Pearson's correlation is 0.6. So it is the correlation is usually a number between 0 and 1, between -1 and 1, sorry. So the correlation is a number between -1 and 1 without units of measure, that measures if they behave in the same or in opposite way, the two variables. So if x increases, then we expect that also y increases if it is positive, if the correlation is positive, or decreases if the correlation is negative. So, for instance, here, if x is bigger, we expect y to be bigger because I've generated it. So in real life, you see only the data, and you can estimate this correlation. I mean, you can compute this correlation, but it is an estimation of the real correlation. So we have also a test to say that whether or not this correlation is different from 0 or not the real correlation. So the sample, the one is for the one we can observe from data because we don't know the mechanism that generates the data. The one of the sample we can observe it is always different from zero, unless unless very particular cases, which is which do not happen for real data. And so we need a test to say whether it is significantly different from zero or not. So to decide whether the mechanism that generates the data generates correlated or uncorrelated data. So there is also the Spearman, sigma, and the Kendall's tau. These are the advantage of the last two variables, of the last two correlation coefficient. The coefficients is that they don't need like the data to be linearly dependent. They are able to catch arbitrary monotone behavior, like it could be that y is equal to x squared plus x to the power 4 plus an exponential, and the like the Kendall's tau or Spearman's correlation will give better results. So we can try to compute the Spearman correlation and the Pearson's correlation and see the difference in this case. So let me, sorry, I didn't, haven't updated my variables x and y, so it was, now they are like more like this. And let's try to see. Okay, still the Pearson's is higher. I don't know why. Okay, probably let me take a mean, which is like 3. So now it should be more clear the quadratic behavior. Yes. So like let's try to see both. Well, you see, in this case, the Spearmans give you a value which is almost 1. And indeed, like looking at the plot, you expect them to be really correlated. But you see that the y-axis is travels on a different scale magnitude. So actually, this is more quadratic than it seems. And the Pearson's correlation doesn't fully catch this quadratic behavior. Instead, the Spearman, or the Kendall's also. Yes. So this is what we did last time in brief. Now we will do regressions. So please, I mean, if I say something that you don't understand or you want me to repeat, just ask. Or you. So okay, the topic of regression is well, it is a way to relate many variables. In this case, we will start with 2 variables. So we start with bivariate regressions, and in particular, we will do the linear regression because we will not have time to do other kind of regressions like logistic, but probably we will do generalized, sorry, mixed effect models, which is a good topic. So bivariate regressions, so we have 2 variables, x and y, and we take some samples. So we observe them as usual. These are random variables. We can observe them. So we can observe x1 so n is the sample size. This is like the first the sample from the first variable. And we have also another variable. So if we want to give a linguistic example, I don't know, x can be like so x can be like the age of the informant, and y can be like the number of lexems of words known, words, sorry, yes, words known. Or for a more classical example, x can be the weight person or height of person, and y the weight. Um, so the important fact is that here xi and yi refer to the same observation. So this is very important. And let's, I mean, regression is not only used to predict the variable y, but let's try to give this problem. So we are asked to predict, to guess the variable y, let's say. Okay, for instance, let's take y to be like the height of a person. So, and let's say that this height is taken from a population like of from a set population which can come from, say, Moscow or Amsterdam. So let's build this population. So the city can be Moscow or Amsterdam. And I'm saying Amsterdam just because people there, I've heard because I don't know anyone from Amsterdam, but I heard that they are very tall. So we will put a bigger mean in Amsterdam. But now let's take a sample of, let's take, we have the number of informants, sorry, the population is of size, let's say 10,000, okay, 1,000, let's say. And let's say they come from these cities, we assign a random city to each informant, sorry, to each member of the population. And we are selecting some cities. Let me see this work. This should work. This should work. Okay. Okay. City. Sorry. City. Okay. Now we save this in a vector. Okay. I save this in the vector city. And so city is the vector with only Moscow and Amsterdam, and sample cities is a long vector, which are the cities where the population that tells us where the member of the population lives in Moscow or Amsterdam. So this is city char, and since usually categorical variable is saved in factors, let's transform it to a factor, so as factor. So let me use also tidyverse. And save this vector. Okay, it's not working. Yes. Okay, I don't know what. Okay, of course there is no output. Well, now I generate some random data. So let's say um, where the city. So the vector of heights. Let me initialize it as a vector of this size and population, and the mode is numeric because it's a vector of numbers. And then I assign to each informant, like living in, say, Amsterdam, I'm assigning like a random uniform random variable. I have to sample this number. So this sum gives me the number of people that live in Amsterdam, and I multiply it by, say, 10, and I sum like 100, say 180. They will be really tall, no, too much, too much. So 175, and I do the same for Moscow. But we will put here a more standard height, which is 170, plus something which has mean 5. So it will be, I guess, I mean, this is random data. So for the city as factor, city chart. Okay, now I should be able to plot x against y. So I use, so let me put everything into a data frame.
So basically, when we say отрицать что, что.
Okay. Sorry, but so I need to put here the city and the heights. So now I should have my data, and now I can plot it. Okay, now there are a lot of people, so these look like lines, which makes sense. So let me decrease this number like 20. So, but let's say it's a big number. Okay, let's imagine it as a big. So Now, we are asked to like this. I don't know. It's like an event, in which both like people from Moscow and from Amsterdam are participating. Let's say. So I don't know why now it's not working. Okay. So and we are asked to compute to predict, to guess the age of a randomly chosen person. So let's choose a person randomly. So sample from this data frame. So data, we sample one person. So let's see. Okay, we have this guy from Amsterdam, which is this matched out. So let's say that we don't look at it. So let's sample another one, but let's save into the variable guess height. What so guess? No, let's say to guess because we have to guess it. So what can be a good prediction for y? So without knowing anything. So um, so the question is, what is a good guess? What is a good guess? So there are not like there. We need to define what is good, but for sure, like let's call the guess at y. So whatever definition of good guess, like this prediction will be bad because no, or -5, it's impossible. So there are many guesses we can make. We can take the mean or the median. So there are there are there are many guesses we can make. Um, so we can take, for instance, the mean. Let's just simply take some guesses. So we can take the mean of the vector heights, because we don't know if this guy is from Amsterdam or from Moscow. So we can take the mean, we can take the median. Should be very similar, pretty much similar, yes. So which one is better? We need a notion of what is good, what is bad for a prediction. So uh, the idea is to one possible way to decide which prediction is better or worse is to give a penalty, to define a penalty that makes you pay if you are wrong. So how much do you pay if you're wrong? So a possible way to say what which prediction is wrong, is worse or better, is to define a penalty for being wrong. So possible penalties, well, are we can take so if y is our variable, we can take y minus our prediction, which is called y hat. and take the absolute value because penalty to pay has to be a positive, let's say. So this is a possible penalty, and also y minus height y to the power of 2, for instance, or whatever other function. These are two possibilities. Okay, so and let's see in this case, let's try to use the first notion of penalty. So we have to take the absolute value of y 8 minus our guessed y. Let's take first the mean. Or the same stuff with the median to see which one pays like is worse with the first function. Okay, y is not found this data. Okay, no, it's not data, it's the sample, it's the to guess. Okay, I called it in this way. So let's run both of them. You see, like the median is better in this case. And let's see instead the second one. If we use the second function, so what is the second function? Well, it is the height of this guy minus our mean, let's say, and to the power of 2. And to compare the two predictions. So let me do the same stuff, but instead of the absolute value, we take the power. So now, like still the median is better. Okay. So, but it's a little bit well. Now it's yes. Okay. So this is to say that to give like a notion of good prediction, you need one possible way is to define a penalty. Okay. So now coming to the topic of of actually giving like a guess. Well, uh, let's okay. We let me give you another characterization of the mean. So, like, assume we want to do the same. So, okay, we had this population which consisted in people chosen from two different cities with different heights, and well, uh, we want to make a prediction on the height of a randomly chosen person. So there is this other characterization. So we give a penalty, but and we want this penalty to be small, as small as possible. Now, this is a random quantity. Why? Because this y is random. So let's define, and I want the penalty to be like deterministic. So if I know the distribution, I want to give a precise number, not a number that depends on the sample. So let's take the mean of this quantity here. So we do the same here, but instead of taking we take so the above the above functions penalties are random since they depend on the chosen person. So we take the mean. Let's say a possible choice is to minimize like mm, so for instance for each y the best prediction would be like y. So this is not what I want. So the best prediction in this case, in that case, will be exactly y equal to half y. So half y equal to y. But so we don't know why. So we want this guess to be independent from y. So we simply take the mean of the above stuff. So let's say we take everything here, copy and paste, and instead of doing this for for an element, we do it for each member of the population, and we take the mean. So let's put here data. Why there was an absolute value here? Ah, okay, here I had, okay, it's the same without the absolute value. And then we take the mean, because this is a vector now. And now you can see how which prediction is better in using the two functions in mean. You see, comparing the first two the first two results, the prediction is better to use, sorry, using the first function, which was the absolute value. It is better the prediction of given by the median. In the second case, it is better the prediction given by the mean. Slightly, but it is a notion. So it is, what I want to say is to define good, you need a notion of a way of comparing stuff, and this is a good way. So if this also explains one thing, that the median is less outlier dependent. Why? Because okay, this is not by chance, because we have this proposition. Proposition the mean is of a population which can be either a real population or a random variable, an abstract population, is the number is characterized by being the number mu such that the expected value of y minus mu to the power of 2. So what we computed above is minimal. So this a function. So this quantity here, if we compute here any other, we can do this again. So we can take the mean of beta heights minus whatever number, let's say 175 to the power of 2. This proposition guarantees that here I will obtain a value which is smaller than 16.3, so which is higher than 16.31. So let's see, 19. So let's try 178 just to check that is again bigger than 16.31. So yes, this is a fact. It's easy to prove, but it requires to simply to differentiate. And another proposition is the following, that the median is the number that that minimizes the this quantity here. The absolute value is the number that minimizes this quantity here, the quantity among all the mu in the real numbers. In other words, if I take like here, again, I take the mean of the absolute value between the eights and let's say 178, I should obtain a number which is bigger than 3.37, sorry, 3.39, which is bigger, even not that much bigger. So here, whatever number I place here, 178, 179, and it will be bigger than this number. Okay, so the penalty you pay gives you the prediction. And by the way, this explains also why, like, the median is outlier less dependent from the outliers, because you pay less. Like here, if you have with this function, if you have an outlier, you pay the square. I don't know if you have a guy which is tall 2 meters, 200 centimeters, and your guess is 179, 180. Here you pay 20 to the power of 2. So it is better to choose a mean that is higher. Instead, here you pay only 20, not 20 to the power of 2. So that you pay a little bit less for the outliers, and the mean is not really outlier dependent. So you can check it by doing uh, some putting some numbers, taking the mean, putting outliers and the median, and see how they behave. So okay, this quantity here, the mean of so this quantity here is called so the mean of the population minus your guess is called the least square, no, the square error. And the estimator you obtain by minimizing the squared error is the least square estimator. Okay, so this is like what, and the linear regression will use this estimate. Sorry, the square here is important. Sorry. The linear regression will try to estimate, will try to minimize this quantity here. So there are other functions, but we will use this function. Okay, now, so up to now, we have not used the information of the variable x, the city. So if you observe it, so let's observe it actually. I don't know which city we have chosen. So to guess city, it's in Moscow. So we have chosen the data. So in such a way that Moscow citizens were like shorter. So let's try to compute the mean. But now we have this additional information. Now, like we our since our state of knowledge has changed, so our state we have observed x equal to Moscow. Now the variable y equal to heights has changed its distribution, because we know that I've chosen it. Now we are in the second case. It's like this one. So since our state of information has changed, we know that this data is generated according to this command here. So no, we know only the data. So we cannot look at this data, at the precise way in which this data is generated. But we have like our sample. So we can make a new estimate which is better. So we can do a better estimate with this knowledge. We can take the mean of to guess sorry, the mean of the data of the heights, but from the people living in Moscow. Okay. Okay, it is a square bracket that I have to put here. Expected. Okay. So this is a better guess. And indeed, let's try to see this this guess. So, uh, like to guess if it is true or if it is better. So let's see. Try to see it. In this case, let's try to see also the mean, the total mean, like the mean. Okay, in this case, it's not better than the guess we would have done without knowing the city. So, but it's a case. Let's try to draw again another guy. So we choose another guy. Let's try to see if he's from which city is he from? Amsterdam. So we need to replace here Amsterdam. The guess is 179. He said is 181, and the guess without knowing which city is he from is 176. So much worse. So the moral is that we can use the information on the variable x to make better predictions. So keep in mind these two facts, and then we will do the linear regression properly. So this fact, we want to estimate y using the mean least square method. And the mean changes after we observe the data x. Okay. This is like a big introduction. So this is like up to now we haven't done any regression. It was simply about data generated according to some mechanism, and if we observe one data, maybe we can infer something on the other. So let me okay. So maybe let me like write a better way this last fact that the mean changes after we observe the data. So conditional distribution, let's say, conditional distribution of y given x. So if we observe so do you have questions concerning this? So if we observe x equal to x, then the distribution of y changes, and so if we take we denote by this symbol here, the expected value, the mean of y provided x equal to x. So the example is what we did before, so I plot it again. And let me also, okay, no, yeah, I will plot simply this one. So the distribution chain of y changes if we know the variable x. So you can see it from here. I mean, I've generated it, but so that I know it in advance. But also, if you don't know how it is generated, you can discern these two different behaviors, and the mean changes. So as also our prediction depends on x. And we want to take our prediction the mean, because we want to minimize our least square method. So we want to use our least square method, so we want to minimize the square. So this quantity here is actually chosen so as to minimize. This is a mean, so this is a mean, so that for each x, and it's a function of x, because depends on the value x assumes. So for each x, this quantity minimizes the above quantity the square. Among all the mu. So for sure, so if I choose another mu, it will be bigger. So for sure, this prediction will be better. So for sure, the prediction the mean of y minus our prediction will be better. This is like will be greater than is the best we can do. I mean, okay, this is all theoretical. Now let's try to introduce a model, which is the linear regression, which gives you a specific form for this value, because we cannot compute this mean for every x unless this, in this particular case, in this simple case. So let's introduce the linear regression. So the model. Mm, the model is the following, that y is equal to beta 0 plus 0 plus beta 1 x plus some noise, mean zero noise. So this is the model, usually Gaussian. So if we want to have the right p-values, it is Gaussian, but okay, let's use a Gaussian mean zero noise. Now, y can be, as usual, if you want to use linguistic data, it can be like the number of words known, and x can be like the age or whatever, or the degree of education or whatever linguistic data you want to put. Now, I need to do two stuff now. Why this model is important, why this model makes sense, and two, why how to estimate so what advantages it gives to us. And three, okay, how to do inference on this model. So remember that in the first lecture, I was giving you models which are a little bit unrealistic, like informals that use the formal or informal variant of a word, like tossing a coin. This is unrealistic. Nobody believes that, but this is a price to pay for our lack of knowledge. So this model makes sense because it is an empirical relation. This model is an empirical relation, which is, for sure, it is false. No way one can prove it false. But the idea behind it that makes sense is the following: uh, like the the main uh, the main thing we would like to do is to find a relation, to find like variables x1, xn, many variables like these ones, maybe linguistic, that can be like, I don't know, like the degree of education of a child, the time spent on books, on television, on other stuff. We would like to find a relation among all these variables and y, like the number of words that the child knows. So we would like to have something like y to be a deterministic function of the other variables. Probably this is not possible, but maybe like getting a lot of data from this child, maybe we would like to have this kind of deterministic causal relation. So I give you like all the data of the children, all of the particular child chosen, and I can tell you exactly, precisely what how many words he knows. Of course, this is impossible, and what do we get is that is we take since we cannot know every possible variable, we take some only in this case only one of it. So we take y and x. Y is the number of words and x is the age. And all the other variables that the price to pay for this lack of knowledge is to put a noise, like some stochasticity. This stochasticity arises from the fact that we don't know the other variables, and we say, okay, maybe if the age, if he's 1 year old, maybe we take yes, we don't know the other variables, and we put a random a noise, like a random variable, some stochastic, and we model it with probability theory. So this is the idea of putting this model. And what do so we lose like what we would like from science, like to give you like answers like of the form like, okay, this function f would be like very interesting, but probably doesn't even exist. So what we lose is like causal relations and other stuff. But now, what do we gain? We gain that with this model we can like tell stuff. We can basically tell that we can estimate the coefficients. This model is an empirical relation that models that accounts for the lack of knowledge on all the variables, on many variables. Uh, we think so. Okay, and what advantages is give to us? We can estimate it is interpretable. So, what is the interpretation of beta one, for instance? Beta one is like the number of words per year, let's say, equal to the number of words per year. This is quite interpretable. Then we can infer from data beta 0 and beta 1. Then, and if the model is to some extent better than, I mean, it is better than not having anything. So if it is good, we can use it to do prediction, to make predictions. So these are the advantages. And now let's try to estimate beta 0 and beta 1. So we use, okay, this is the theoretical part. Now let's go to the practical part. So estimate beta 0 and beta 1. So since the noise is mean 0, the model tells us that the expected value of y minus so our prediction takes the minimum at this function here. So this function here, beta 0 plus beta 1 x minimizes the least square error. So this is, I mean, actually I have proved it, but I mean, you don't need uh, to review the proof because it was really fast, but it is in the lines of what I told you. So because why? Because this noise is mean 0. So like this is linear. So I mean, this is the mean of x. So the mean of y given x is simply this one. So the mean minimizes the least square. So our prediction is this one, the one which this is equal to the expected value of x given x, which is a function of x because we observe it and then the distribution changes and then the mean changes. So it depends on x. So this is a consequence of the model. To estimate this function, we therefore try to minimize this quantity here. We take this function here, which depends on x, beta 0. Okay, let's call it with another name. So tilde beta 0 and tilde beta 1. Which is equal to tilde beta 0 plus tilde beta 1 x. And we want to find beta 0 and beta 1, tilde beta 0 and tilde beta 1 in such a way that this quantity is minimal. So that y minus at y to the power of 2 is minimal. So maybe let's take a break, 10 minutes break, and then try to minimize this function and maybe not by, I mean, we will see that R does it automatically, and then we will see that giving other values, this quantity, which depends on beta tilde 0, which is the intercept of the line, and beta tilde beta 1, this quantity is a function, let's say g of, of, of beta tilde beta 0 and tilde beta 1 attains its minimum value at beta 0 and beta 1. And to estimate this, therefore, we take, since we only have a sample, we can compute this quantity only where we have the sample. So we will use that fact. So let's, okay, in the next hour, we will try to minimize this function when we have only the sample. Okay. So if you have any question, I'm here to answer. So see you in 10 minutes. Okay. So if you have any questions, please tell me. That was the mathematical part. So what I was saying is that yes, if we have the following model, so we have data that is has this structure, x plus some noise with zero mean. Then we have two things. This is the like the sum of what I did last in the last hour. So that the expected value of y given x is equal simply to beta 0 plus beta 1 x. So if we observe x, then we expect y to have this expected value, and this is due to the fact that the noise is zero mean. Then, and for the properties of the mean that we said in the previous lecture, so the fact that the mean minimizes the squared error. So it is not that the mean minimizes the squared error. So if we center the squared error in the mean, we obtain the minimal value for the squared error. So in this sense, it minimizes the squared error. For the properties of the mean of minimizing this quantity here, the expected value of y minus mu for each x. So let's call it mu of x. For each x among all the mu x this is only a notation, the X, in math.dbr, so I could also have avoided writing it, but I can also write it. So for each X, then you can find beta 0 and beta 1 minimize this function that I have called G. Minimize the function y minus the prediction of y made using beta tilde 1, beta tilde 0, sorry, and until the beta 1, and of course it depends only on x, also on x, because this y hat is defined in this way. This is a function which depends on beta 0 until the beta 1. So, and I need a square here, sorry. So, just the theoretical part. Now we download some data and we try to do, so let's use, I don't know, the data about this data about students. So it is the more standard one. Okay, I can pass you also the other ones, which are like the data, linguistic data. So you can try to do your own linear regression, which is quite good actually. So a quite good thing to do. So I will put it in the chat. So let's observe this data and you know, let's save. So we download this data, then we look at its column names. What happened here? We select the numeric column. So select from educ. We select like let's look at the call names. Well, let's take only reading and write and reading and math. Okay, now let's also take only 20 of them because so we can plot it in a better way. 13, let's say, 10. And we save it into the variable educ2. And we plot it, ggplot. And we also give a guess for the beta 0 and beta 1. So let me first run this chunk of code. Okay, we see these points here. We try to give also a guess, a prediction. So at y, we fix a beta 0, beta tilde 0, let's say. Let's call it, and let's put it like 2. And at beta tilde 1, and let's give it the 1, like 1, it's okay. And hat y will be simply the function that takes in input the value of the x. X in this case is the reading score, read, and takes in input also a beta, a tilde beta 0, and a tilde beta 1, and gives me back simply returns a what? Well, beta tilde beta 0 plus tilde beta 1 times read, the reading score. And we add to the column educ2 the prediction made with this hat y. So let's take data, so educ2 predictions. We place here, well, hat y, and we need to pass the reading score, so educ2 read, then our beta tilde 0 and beta tilde 1. And we plot also geom upline, the line with slope equal to beta tilde 1, and with intercept equal to beta tilde 0. So let's see what's wrong with this code. If the, okay, at y is okay, I have to run everything. Incredibly, this chunk of code is correct, and so I predict, I gave like some random numbers. Now, so these were placed by me. Now, how to choose the best ones? This is the point. So these are pretty good actually, because it looks as if they are good enough. So let's take a bigger sample, let's say 20. To still good, okay. Well, how to choose the best values for beta 0 and beta 1. So if we knew the distribution, of y and x, we could minimize the function g, the one which I have defined from the model, this g beta tilde 0, and this would give me the correct ones. Since I don't know the distribution, but I know the sample, I approximate G giving with the sample. Which was underline X and underline Y. So the sample is the one that I plotted here. So like you can think that there is the whole population of abstract population of students that have this reading and math scores. And here it's only a sample of them. Now, how we can approximate this function here? Well, I can take I take the sample which was, let me write it in a better way. So was x1, L dots xn was a vector of n components, and is the sample size. And yes, we estimate the function to minimize by the sample mean. So g beta k tilde beta 0 and which this function was approximated by the sample mean. This is actually a consequence of the law of large numbers. So the sum between of the difference between the square differences between the sample and hat y. So what is hat y of x1 beta tilde 0 and beta tilde 1. This is the first to the power of 2. This is the first residual. So let me call it in a better way. And then I have to sum everything. So each residual. So okay, good. I need to put here a parenthesis. And I need to do this for each point. So also the last point, y, n minus the prediction. So this is the function to minimize, and this is everything in this function can be computed because we know y1, x1, yn, xn. Beta tilde 0, beta tilde 1 are the variables of the function that we want to minimize. Then we simply, the computer gives us a way to minimize this function. And this gives me an estimate for the real beta 0 and beta 1 of the model, the ones without the tilde. So the minimization, solving the minimization problem gives me an estimate for the beta 0 and beta 1 of the model. So this is as simple as that. Now, a little bit of notation of nomenclature like yi minus the hat y computed at xi and at the true value actually. So beta, okay, tilde beta 0 tilde beta 1 is called the residual, the ith residual. And so we can restate, usually it is said that we are minimizing the squared sum of the residuals. So let me plot the residuals. These are simply the signed difference between the real value and the predicted value. So let me simply place them here. So let me add to this plot, let's save it in plot, into the variable plot, and then plot is equal to plot plus what? Well, I need to do a segment, so geom segment. I need to put the variables x, which is equal to read, y, which is equal to math, then sorry, then there is x end, which is equal to x, to read, sorry, and y end, which is equal to the predicted value, which is hat y, it is Fred. So, and then let's see if this is correct. Yes, and let me see, and let me plot it. Null, okay, y. Okay, and maybe let me color them with red. So the residuals are okay. Why on the x on the x? I mean, why the points are really well? You see that here is like kind of quantized, like these are results of a test. So like there are not. So I mean, you don't see really a vote which is like 4.73. Usually exercise have fixed grades, so it is normal to see many evaluations which are exactly the same, like this ones in the reading part. You see the reading score is exactly the same for many students. And so let me add some jitter maybe mm, because it's nice. So I don't remember, but probably it's, okay. So probably I have to add it here. Y equal to jitter. No. This adds some noise to the plot, I guess, I hope. Um, yes. Well, I now now it should be better. Hmm. Why? Ah, okay. Sorry. Mm, well, I mean, no worries. This is well. I don't know why it's. I mean, here I mean, uh, I mean, here the JIT part worked a little bit. No, okay, no, it didn't work. Well, it's not really important. However, we can minimize these residuals. Um, so we simply and there are algorithms to do them. So the sum of these residuals has to be minimal. And let's do a linear regression. So let's simply R has a command that is linear model, and we place here the formula. We predict y using x. So here we predict the math score using the reading score, and the data is equal to educ. And we can see the result. It gives me the slope and the intercept of the line. And we can also plot it. There is a way to, we can like perform many stuff. Like we can also take the summary of this model. Let me save it into model. And we take the summary. We can auto-plot the model. We need GG45 for this. So let me first look at the summary. Gives me a little bit more information. So it gives me what I called. It is this one. Then the information on the vector of the residuals. Then the coefficients beta 0 and beta 1. Then they perform some tests. I will come back to this. And some other statistics. So we will go back to these quantities. What are these quantities here? Then we can, there is also the autoplot. We need the GG45 for this, which plots me some data, some graphs, and I will tell you later about this. And we can also do predictions. So we have to predict, I don't know, using this model, we can predict, I don't know, a student that takes a reading score of 98, let's say, what is the math score? 80. This is simply the I mean, it's simply, I don't remember now what was it was like the intercept was 21, like model intercept. Coefficient. The one is the intercept, I guess, plus model coefficient. Two times 98. This should give me 80.34. Yes. So this predict function is really easy. But let me plot it, and we can plot it by many means. One good way to do is like geoplot, ggplot, sorry, data equal to educ, and we have to put geom point where x equal to the reading score and y is equal to the writing score, or to the math score, sorry. And we can play like the geom smooth or geom okay, geom smooth probably. If I remember correctly, we have to put method equal to the linear model. Let me okay, I did it before, so I kind of forgot what was the command. So it is like mm, sorry, I okay, probably it was okay, I need here y, I have to predict y using x. Have to pass which what is the formula. Uh, Probably uh, stat of method equal to none. Okay, probably Xeon smooth mapping equal to null, stat equal to smooth, method equal to null, standard error equal to true. Yes, should be this one. And okay, I'm predicting, let's say, math using reading. Okay, now I think it works, but there are a lot of points, so no, no, it doesn't work. Incomplete expression. Okay, here. Right. Okay, probably I simply look for help here. So let me type smooth. Okay, sorry for that. 1 minute, and I need to simply to find again uh, how to do it. Sorry, if anybody of you knows it. Yeah, it should be this one. So method, probably need to write the method in here. Linear model, and this the formula is equal to math given the math score given the reading score. So but the error says that stat smooth requires the following missing aesthetics. Okay, because they have been renamed in this way, but let's try. Still, okay, I can try to put uh, mm, well, um, so probably I should put the statics here, in the top. Nothing here should be fine now, I guess. Ah, okay. Yes, it was only a matter of that one. So yes, you see that this gives me the regression line. So if I can compute the residuals. So like the model gives me also the residuals, which are and we can compare what we did before with what with the residuals given by the one which minimizes the residual. So let's compute the residuals. So we have model residuals. Okay, we can compute these residuals. We can take the square of them and we can sum them. This gives me the sum of the squares of the residuals. Or simply let's take the mean because so this is the quantity that minimizes the linear regression. So let's go back to our guess and let's compute the residuals and see that they are actually higher. So let's go back to here. Let's take these numbers here. Maybe let me use educ2. So let me give sorry, the whole set of points. So I need to predict this quantity here and then plot it. Okay, so now it is the same, and let's compute the residuals. So let's go here. We take the educ, the prediction, the prediction with not the regression line. So these are not the residuals. These are this red, the length of this red segment. Then we take the true points. So educ map minus the predicted ones to the power of 2. These are the residual, and then we take the mean. Okay, they are bigger, of course. So this is an instance that we are minimizing the quantity above the above quantity. Well, okay. So this is actually, I mean, a good stuff, a good check to do. Now, what is the guess that you would make without the variable x? Well, you would guess the mean of y, so you don't have the x variable, so like the trivial guess would be like this one. Actually, you can also implement it because you can guess if you don't want to put the x variable, you can put a 1. So model, the simpler model, let's say model 1, model 2. We take a linear model and we predict with the variable educ, we use we predict the math score using a constant 1. So without using the reading score. We can do this, the same stuff. Well, this will be exactly, let me summarize. Summary of model 2. This now has only the intercept because you don't have the x variable. Well, what are the coefficients? 52. This is the prediction of y using a constant. It's 52. Well, but it's simply the mean of the math score. Because we are using the least square method. So the penalty is the squared one, which gives rise to the median, to the mean. And this 52 is this one here. So let me plot now the same stuff. I copy and paste all this chunk of code here. But now I choose beta 0 equal to 52, and we take an horizontal line to see this simpler model. So I take beta tilde 0 equal to the mean of the math score. And beta tilde 1 equal to 0. And now we run all this chunk code again. Okay, now the residuals are much bigger. And this is like the linear regression without using the variable read. Now, how much this model is worse than the previous one? Of course it is worse, because we are not using a variable that we were using here. In this case, it's really much worse. And the way of quantifying this is given by this summary. In this summary, there is a statistic, which is the R squared, which is the bigger, the better the model with respect to the one without using the variable. And what is actually this one? Well, it is are the residuals. So let's take these residuals. And then let's take these residuals and compute the sum of the squares. So the residuals here. And then we can compare them. So let's take, so first we compute the sum, the squared sum, the sum of the squares of the residuals for the best fit, for the model, for the better model, which we have called the model. So we take the model, we take the residuals, we take the square of them, and we sum them. We take the mean. Then we do the same for the model that doesn't use the variable x. We take the mean of, we have called it actually model 2. But we could do this model 2 residual. We can write exactly the same stuff, and we can take the square of them. These are the total sum of squares, and this is the okay. So yes, this is the residual sum of squares sum, and this is the total square sum. Now we can compute both. So RSS divided by T. So let's plot first, print what are these numbers. So of course the first one is bigger. The second one is bigger because the first one is computed using the slope. So the residuals will be smaller. In particular, if the second one were smaller, then that slope wouldn't minimize the residual, so the other one would be minimal. So it is for sure smaller RSS than TSS, but we can compute the division. So we can divide them 0.56. Now, the bigger, so if in the case this is equal to 1, this would mean that like putting a slope doesn't really improve anything. Instead, putting a slope improves. So this is the more near to 0 this number is, the better the model. So we simply take 1 minus this, and we obtain what? we obtain 0.43, 44. We go back to the model, and well, let's see the summary. Well, the multiple R squared is 0.44. So this is how this multiple R squared is computed. It takes, it is a, measure, a quantification of how much this model is better, considering this variable x gives you a better prediction than not considering anything. So this is good to know. Then there are other statistics, and there is also a test involved. So let me give you like the test. Say what does this test say to you? Okay, so how to say it? Yes. Well, first of all, we are not really interested. Okay, it tells us this test. Okay, so the multiple R squared tells us how much better the model with the variance, sorry, with the slope that considers the variable x to predict y is better with respect to the one that does not take into consideration it. This is the one point. Then the test, sorry, the test that you can see here. So we go back to the coefficients, and we can say that the reading, so the slope, it is 0, the coefficient that goes in front of the read variable, it is 0.66. So first of all, maybe I forgot to say it. This model tells us that the math score is equal to 21 plus 2.6. Sorry, no, plus 0.6 read times read plus some noise, zero mean noise. Y 21 is here, 0.6 is here, and it is associated to the read variable, and the intercept variable is only like a one, vector of ones. This test tells us if so we have estimated our beta 1. 0.6 is the estimate of for beta 1. Is it different from 0 because of randomness, or because beta 1 is really different from 0? So this test tests this hypothesis. So it tests H0 is that beta 1 is equal to 1, to 0, sorry. And H1 is that beta 1 is not equal to 0. So this is the test. Now, we already did this test actually. So all the mathematics involved is basically what, apart from ANOVA, this F statistic, because you see here there is a T statistic. So basically, many tests many tests repeat themselves across different F functions. So they seem a lot, but there are actually not so many of them. There are not so many of them. So let's see where we saw this test. So let's keep in mind this p-value, this t-value, and etc. Well, we have seen this test. Actually, let me write it here. So yes, we can do the core test between the math score, educ math, and educ read. So let's see what happens. Well, t is 12.43. We go here and we see 12.43. So these are exactly the same test. So many tests repeat themselves. Now, okay, so we have said what is the R statistic, sorry, the R multiple R squared. The adjusted R squared is like the multiple R squared, but accounts for it is important when we have more variables, because when we have more variables, it is, I mean, adding a variable is not free in statistics. Maybe if we add a variable which do not explain, which does not explain anything, it gives you a price to pay uh, in the p-values and in everything. So this multiple adjust R squared is a way to take that into account. So if we add like another variable which is independent from the other, it should decrease. So it should, instead, if I add a variable and I only look at multiple R squared, for sure it will increase because the model will fit better the data. So actually I can add here like a normal of the length. So I can add to the data another variable like random, which is a random variable totally independent from the other, let's say of length, educ, read. So, and I can add here this random as a predictor. And let's try to see what I get. This is not a bivariate regression, but it's a multivariate regression. We will see it later. So, okay, now I'm okay. Now, well, you see, the multiple R squared has increased. The adjusted R squared not. so that's a good thing because I'm adding noise. And you can see that the test tells us that they are not correlated, random and the variable y, because the p-value is, the variable y is the math score. So this is basically what I wanted to tell about the statistic that our model gives us. Because the F statistic, you need to know the ANOVA test. Maybe we will do it, but I do not. I wanted to do like other stuff, but it's better to do some exercises better than putting knowledge without um, putting not knowledge, notions without knowledge. So it's better to a little bit of do a little bit of exercises in the next lectures, and maybe I can evaluate them. You can do it in class and then evaluate them. I will evaluate them and put some votes. Then okay, maybe I can tell you what this quantile plot is, because this is a nice way to this nice plot. Or I can okay, no, yes, probably the quantile. It's good to end with the quantile plot. So mm, yes, so the quantile versus quantile plot is a way to uh, uh, so let me go back here. The theoretical quantiles are the quantiles uh, of of a normal distribution. So a quantile, what is? So mm, so the alpha quantile of a distribution X is the point for which the probability, the mass on the left is the point which we will call Q of alpha, for which the mass on the left is alpha. Alpha is in 0, 1. So let me be more specific, let's go here, let's take a normal distribution, let's plot like, I don't know, -5 to 5, we plot the density, the norm from -5 to 5 with mean, we take mean equal to 0 and standard deviation equal to 1. We plot this. Okay, this one is here. This is the density. Then maybe let's take let's be more precise. Okay. Well, okay. So this is the density of a normal, and well, let's try to add a line, sorry, a vertical line at the quantile of order like Q norm of 0.25, and I take the same distribution, so I have to put the mean 0 and the standard deviation equal to 20. And so let's see. You see, on the left of this point, there is 25% of the mass. If I take 1 half, 0.5, it will give me the center of the distribution, because on the left there is 50% of the mass. If I take 0.95, sorry, 0.8, it will be more or less here, probably. Okay. And 0.95, let's say, would be, I guess, out of the, no, it's here. Like 95% of the mass is on the left. Now, the plot, one of the, the plot, theoretical quantiles versus the quantiles, what does it do? Well, it takes alpha. For each alpha, it plots the quantiles on the x-axis, plots the point on the x-axis given by the quantile Q norm of alpha. And on the y-axis, the quantile, the alpha quantile, maybe it's called percentile, alpha quantile or percentile, I don't remember, of the vector of the residuals. Well, what is the quantile of the vector, of a vector? Well, you order the vector, and the alpha quantile is where alpha percent of the vector is on the left, and alpha percent of the vector is, and 1 minus alpha percent of the vector is on the right. So we order the residuals and we say, okay, they more or less, so we can plot an histogram for the residuals. So let me do it. So hist model residuals. They distribute like this. Well, um, so we can take like the quantile, like Q empirical, I guess, the empirical quantile, or the quantile, yes, quantile of residuals. We take 0.5 5, let's say, should be around 0. Okay, residual, sorry. It's around 0, like 50% of the vector is on the left of 0.47. So we can take like the 25, the quartile, the first quartile. So, and we can put an upline, a vertical line where on the x at the quantile at, the, at this point. So we can see that, okay, this, color this in red. So on the left of the red line, there is 25% of the vector of the residuals. Now, how much this distribution differs from the normal distribution? Well, you can get an hint by plotting the quantiles of the normal distribution versus the quantiles of the residuals. So we go back to the plot. Well, here on the y-axis there are the plots of the quantiles of the normal. No, sorry. On the x-axis there are the quantiles of the normal distribution, and on the y-axis the quantiles of the residuals. So you take an alpha, you put on the x-axis the quantile of the associated to alpha of the normal, and on the y-axis you get the quantile associated to the vector of the residuals, and you place a point with these coordinates x and y. So how much it is on the diagonal, this plot is a way to see. So the more these points are on the diagonal, the more similar the residual are distributed as a normal. So this is the meaning of this quantile plot. And then there are other plots, like residuals versus values. So that's is what I wanted to say about all the information R gives using this linear regression, this linear model. So next time I will do like a little bit of. I wanted to give you some exercises, so I'll correct them in class because you need to know. I need to know that you know how to do some programming, and so I will find some linguistic data and give it to you and ask you to do some exercises, and probably I will do some what are called mixed effect models, which are a little bit more complicated because with this, I mean, there is not really. There is also the logistic regression, which is very important for linguistic data, which can be categorical. But I don't have too many lectures, and the logistic regression is not really much more complicated than this. So instead, the mixed effect models are a little bit more tricky. And then I wanted to do the principal component analysis, but probably I won't do it. That's really sad because it's really it would have been a funny lecture. I find it very because it's a dimensionality reduction algorithm, and an algorithm that gives you back something, but you have to interpret that something that it gives you back, because it is an unsupervised learning algorithm. So you say, okay, you want to reduce the dimension of the data and it gives you back some data, and you have to interpret what it gives you back, and so it requires some fantasy, let's say. Then there was, okay, I will not do this, and probably I will do some more testing because I need to introduce like ANOVA, and it can be done through linear regressions. So, and then other exercises. So these are the topics for the last two lectures. No, have a nice weekend. See you next week. If you don't have any questions.